So you've watched James' excellent presentation, you've read the blog, and you're probably wondering, what next? How can I get started with this? The presentation which you're about to see is just one way of you really getting into facial recognition at a relatively low cost. So over to you, William.
Just to check, are you seeing my presentation and me, I suppose?
Sorry, yes.
Good, then I will proceed. Yes, so this work was, this is facial recognition on Google's EdgeTPU. So this was a project that Embecosm pursued largely in the direction of getting teenagers interested in AI. And to try to do this in a way that's sort of intellectually stimulating instead of making AI just sort of this magic thing where things happen. And credit where credit's due, I am not a teenager, though I look very young and beautiful. The two people who actually worked on this project were Pietra and Lewis, two of our younger engineers. Pietra especially did almost all of the work here. Unfortunately, they couldn't be here today to present, so I'm doing it instead. Anyway, so the structure of this talk. I know some of the audience may not perhaps be exceptionally familiar with the neural networks that we applied a lot here. So I'm first going to go over a little bit of neural network theory. I'm then going to cover at least an approach to facial recognition, how a sort of facial recognition pipeline might work in reality. And then I'll talk about how we sort of married these two things together. So how we applied neural networks to face recognition. So first bit of neural network theory, the sort of intuition behind neural networks. And the intuition behind neural networks is that many small, individually simple units can come together to create incredibly complicated behavior. A simple, an individual unit in a neural network is a neuron, sort of analogously to the neurons in my head, for example. And they're just very simple functional units. So in this example on this slide, my neuron is simply taking a bunch of inputs. It's weighting them differently. That's what the W's are. It's applying some function to those, and it's just then outputting it to anybody who listens. You can achieve a lot. Well, you can achieve a surprising amount with an individual neuron, but the sort of magic happens when you combine a lot of them together. A very common way to do this is to put neural networks together into layers, where each neuron in each layer is connected to each neuron in each subsequent layer, but not to the neurons in the same layer. A picture says 1,000 words, and this is probably better than my explanation. So it's all very well to say that and to sort of get to say that this complicated behavior arises, but it's probably better to sort of give an intuition as to why this happens. It's easy to say lots of simple units come together to create complicated behavior, but how does that actually work? So a simple intuition here is I have hand-drawn this terrible function here. It would be quite a horrible function to approximate by just sort of throwing polynomials at it to try and work out what fits best. But actually, if we just put a bunch of simple straight lines together, a bunch of simple linear functions, we can approximate the function quite well. And that is a way of thinking about what the neural network is really doing under the hood. A lot of individual simple units are coming together to create complicated behavior. A thing worth saying is that if we are willing for our individual units, our neurons, to be more complicated themselves, I will probably need less of them to do any given task. So here I've tried to use simple curves instead of straight lines to approximate the line, and it was much easier to do. I needed far fewer. Yes. So that's an intuition as to how the neural network sort of functions in a sense, as to how the neural network can achieve complicated things. But the question is, how do I take this framework and then actually make it do that for something useful? How do I adapt my neural network structure to be what I want it to be? A very common way of doing that is with backpropagation. And backpropagation is basically just a simple credit-blame assignment system. And so in backpropagation, the amount that a neuron contributes to a correct or incorrect solution corresponds to how much it is rewarded or penalized for that. So the intuition here is that I feed some things into my neural network, see what comes out, and if it's correct, I reward it, and if it's incorrect, I penalize it. So simple example here, I have 3 neurons feeding into a correct answer. I have lines of varying thickness corresponding to how much they each contributed to that correct answer. And then what backpropagation will do is it will proportionally reward them by how much they contributed. So the bottom one that contributed a lot to that correct solution is upweighted a lot, and the top one, which didn't contribute much, is barely upweighted at all. A similar thing applies for my incorrect solution. So in this case, I've got it wrong, and I want to penalize my neural network because it's done the wrong thing. In this case, I penalize my bottom neuron very heavily because it contributed a lot to this failure, and I don't do so much to the other 2 because they didn't contribute so much. And by doing this many times, backpropagation forces the neural network to organize itself around what you want it to do. So we go back a few slides. By increasing the weights of correct solutions, I then make my neural network be more correct in future. And by repeating this many times, the network organizes itself to come to the solution I'm trying to get it to do. So this gets a little bit more complicated when we have many neurons. Obviously, this example is nice and simple, but when we've got a large number of interconnected neurons in multiple layers, backpropagation becomes a bit more complicated. And in general, what I will do in this situation is that I will sort all of the backpropagation for one layer out at once, and then I will propagate that error back to the layer before that, and so on and so forth. An interesting facet of this in neural networks in general, particularly larger, longer neural networks with more hidden layers, is that neurons earlier in the network, closer to the input, won't contribute so much to the final output, and so this backpropagation algorithm won't penalize or reward them very much. And so in order to effect any reasonable changes to these, I will need I will need to do this many times, possibly a prohibitive number. And we call this the vanishing gradient problem, and the deep learning that a lot of people talk about is basically largely attempts to solve this problem. But anyway, that was just a little aside. So that's hopefully largely covered some key neural network theory, and at least giving an intuition as to why they are useful tools and why everybody raves about them so much, I suppose. Next, I'm going to try and cover the basics behind face recognition, or at least a way that face recognition works. I'm sure you could make it work other ways if you wanted to. And the way we're going to do this is we're going to take an exemplar picture here, which I have here, and we're going to look at how we would take the faces out of this and try and identify the people inside them. I did pick this picture for a reason. It's quite a nice example in many ways. So the step 0, the sort of step you should consider, well, I'm not even sure if it really counts as a step. The thing you should perhaps consider before everything else is, does my picture have any faces in it? And you can check this. Perhaps it's an assumption that you can make because you know that you're only going to ever be given pictures that have faces in them. But it's a thing that's very much worth considering before you go on to any other steps, because obviously if your picture has no faces in it, then there's not really any point doing facial recognition. So I have this picture. I want to identify the people in this picture. So the very first step is to, oh dear, these have gone rather out of line. The very first step is to identify where the faces in the picture are. And the important thing here is that's all I'm doing. I'm just trying to find where the faces are. At this stage, the faces are probably going to be different sizes. They're going to be different orientations, such as the lovely chap lying on the floor there is oriented rather differently to everybody else. And in general, I'm only solving one problem here. I'm just finding where the faces are. That's my first step. My second step is to transform these faces into a uniform input, to provide the best possible chance for my later steps to fairly treat each individual face as possible. So here I will orient the faces, I will resize them to all be the same size. I will perhaps mess with the contrast of the pictures to make sure that there's enough contrasting pixels to make a reasonable inference, and so on and so forth. Finally, once I've done this, I do probably what most people would call the difficult bit, which is creating an embedding of the faces, basically extracting the features from the faces so that I can make a sensible inference about them. So if you or I look at a face, we will see features like perhaps you'd see my eye height, how high my eyes are on my head, how high my eyes are on my head as a key feature to identifying me as me. But and this is an analogy to what's being done here. We're trying to extract features from the faces, but very often they won't be human recognizable features. These features will be probably chosen by some machine learning algorithm to be the features that give them the best results. And so they'll probably tend to be things like lines or particularly notable patches of pixels, and so on and so forth. But the important thing here is that I'm taking my sort of difficult structure that is an image in RGB and converting it to a vector of numbers that I can then practically do stuff with in a mathematical sense. And once I have that vector of numbers, things are rather easy. I basically take my vector of numbers, stick it into my favorite machine learning algorithm, machine learning happens, and then I get an answer out. That's just you can just deploy whichever of your favorite algorithms you would like here, and get the solution. So hopefully now we have covered at least the basic intuition behind what neural networks are doing, and we have covered basic intuition behind how a facial recognition pipeline might work. So now I'm going to talk about what we have done. And what we have done is that we have taken some specialized hardware, in fact Google's EdgeTPU, and we have tried to build a facial recognition pipeline largely supported, or hopefully eventually entirely on this TPU. The reason we want to do this is because a motivation for using specialized hardware, in this case like the TPU, is that neural network operations require a lot of very specialized, they require a lot of processing power and use a lot of very specialized particular operations when they're being trained or when they're doing inference. So it's very beneficial to use specialized hardware for this, makes things go quicker. So where open source comes into this is that actually the TPU and nearly everything associated with it is entirely open source. So TensorFlow, which since Google's baby is TensorFlow, the EdgeTPU works with, is largely open source. A lot of the machine learning AI libraries that we'd wish to learn are open source in Python, so on and so forth. So as I have been explicitly saying, mostly open here. Obviously, the specific hardware specification of the TPU itself is somewhat closed, as are some of the details in TensorFlow about how stuff is compiled and in the architecture, presumably to keep that as it. So not quite everything is open here, nearly everything is. So we have taken this EdgeTPU hardware and we have tried to implement a face detection pipeline on this hardware. But we are somewhat limited with what we can do with this TPU. So one thing we can't do is we can't train our neural network on the TPU. We'll have to train it off the TPU and then bring that trained model onto the TPU. Training it is frankly difficult, and this small piece of hardware doesn't support it well, so it's simply not practical to do. In terms of our facial recognition pipeline, at the moment, we are only doing 2 steps of our 5 possible steps, I suppose, or at least the 5 ones that I proposed on the TPU. So we are leaving detection, localization, and transformation as things to be done off the TPU, sort of on our large machines, and then we are feeding the TPU only the the properly transformed unified faces for embedding and then classification. Though we will make some small changes to that later. If you're wondering how this sort of practically works, broadly, you take your favorite TensorFlow model, you train it, you then export it to a particular format that the EdgeTPU likes. This gets compiled down, stick it on your TPU, the TPU does its magic and works for you. So we have the specialized hardware, we know which steps we're doing on the TPU and which steps we're doing off of the TPU. How do we proceed from here? So the first thing is that we needed a trained model that we could put onto the TPU to then do stuff with. The easiest thing for us to do in this case, and what we did, was to take a pre-trained model for, I think, object classification in this case, that we knew would work on a TPU, and then retrain it to work on faces. And we did this with the Casio web-based dataset. It's a pretty large dataset, and certainly it was easily large enough for our purposes. And as I said, we didn't do this on the TPU board. We did this on one of our big build machines. And it took a while, but it got done. And in this first iteration, the neural network was rewarded for, we effectively trained the model to identify faces, this neural network to identify faces straight up. So it was effectively doing the embedding and the classification steps together. It would create an embedding and then it would classify it based on that embedding. Will be one way to look at it. So this worked surprisingly well, perhaps unsurprisingly well, I suppose. We were seeing about 70% testing accuracy, which was pretty good. But training the model in this way came with at least one major problem, which was that the model really didn't generalize well to faces outside of the training set. And this isn't ideal. It would be nice if we could train a facial recognition model that would work on faces not just inside our set, but could easily be adapted to faces outside our set, because it's difficult to train models. It takes a long time. We don't want adding faces to our set to be difficult. And to solve this, we used a technique called weight embedding. So essentially what this involved was training the network as before, and then splitting the neural network at the point that it had generated embeddings, and then training a new classifier, which in our case I actually believe was another very small neural network, to classify based on the embeddings that the first network had generated. And the advantage of doing this is that the first network is trained to generate general embeddings that work well, and the second network is trained to use these embeddings to do things. And because the second network, or whatever you choose to do, is much smaller, it's much easier to retrain the new data. I believe we were able to tentatively retrain our network on new identities and have it kind of work within 5 to 10 samples, with 5 to 10 samples of a new face, have it identify that person. Though more formal testing on that will be required in future to quantify exactly how well it is work. So that's about where we're at with this. I have talked a lot quicker than I intended to, so I got through this very quickly. I do apologize. Where we're looking to take this in future is that if we go back a few slides, where at the moment we're doing only a little bit of the whole face recognition pipeline on the TPU, and frankly the easy bit, it would be really nice if we could do just the whole thing. So have the GPU detect whether there's a face, have it pull that face out of the image, and have it normalize that, transform it, and then do classification on it, recognition on it. That would be nice, and that would be something we'd like to shoot for, and doing this in real time, perhaps with a connected camera, would be nice. That's the direction we'd like to take this. We'd also like to try and take advantage of this weight imprinting technique a bit more. It would be nice if we could train our pipeline to take a new identity and very quickly learn about it, and then apply that in the field very quickly. I said that the TPU wasn't really suited to learning, but actually I think that if you only need 5 or 10 iterations to learn a new identity, it probably could do that, which might provide a way of adding new identities to the model without going through the laborious process of training again. Finally, a common topic at the moment with neural networks is that they are biased. Something we particularly noticed in our data set was, and something that many people have noticed before, is that dark skin makes it very difficult to do accurate classification because of the lack of contrast in the picture. I know Pietra is particularly keen to explore this and the implications of this. Anyway, that is the end. Do you have any questions? Suppose we're doing questions at the end, so that was a silly question.
Right. Don't appear to be any questions.
Suppose people can't. We're doing the question section anyway. I shall hand back over to you.
Okay. I was going to say I haven't quite figured out this questions widget box yet, but it doesn't appear to have any questions. Okay, thanks for that, Will. That brings us, I think, to the end of our session for the night. Let me get this one back. Change presenter. We might get our, okay. So we should have that back again. Yes, this is what we're going to talk about next. So I'd just like to thank our two presenters for their great talks this evening. I'd like to thank James Ferriman of Reading University and Will Jones of Embecosm. I thought they were two great talks, and hopefully they will whet your appetite for more, in which case don't forget about the blog post, which you'll find on our website. So what have we got next? Okay, on Thursday the 17th of September, we have a Women in Open Source meeting, which was rescheduled from April. And Thursday the 15th of October, we're going to have a lightning talks evening and AGM. Given the current COVID crisis, it's likely they will be online. More than likely they'll be online, actually, I think. So I'd also like to thank people who've helped behind the scenes, like Kerry, Sarah, and Jeremy, and all the other people. I'd like to say a big thank you to them. And finally, I think, don't forget, you can watch this again on our YouTube channel in a few days' time. I think the link to that will be going up on the website, I think, within the next few days. So, okay, thanks to our presenters, thanks to you, the audience, and just remains for me to wish you a good night, a pleasant evening, and I hope you enjoy the rest of your day. Thank you.